can test it out. We are live. Make sure the sound's good. Should be good.
Nope. We're alive.
Okay, just wait a little bit and we can start. All right, hello everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
Sahil, welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, we would ask that if you're on YouTube to post any questions or comments during the episodes, we can get to them. And then afterward, if you haven't joined the Discord channel, please do join it. And lastly, if you're listening to this on a podcast, wherever you get your podcast from, do leave us a review and give us whatever star rating you feel that is adequate to describe and correlate with your review. So without further ado, let's get to it. So I guess, Tim, when I saw this question, I like what came to mind was this like giant cosmic highway with just like speed limit, like something. And I feel like if I went faster, and the physics police will come and like say, hey, you're going faster than the cosmic speed limit. Will that happen, or is it something completely different?
I think to some extent you can kind of think of it as a cosmic police, but it's almost more like your car just wouldn't get that level of performance. I feel like because I guess unlike ordinary laws, these are laws of physics. So no matter how hard you try, you actually can't get to the speed limit, which happens to coincide with the speed of light. But I think we want to explore a little bit more to the why. Like obviously physics is a practical science. Like we know the speed of light ultimately comes when you do experimentation, you test different particles, and you see that hey, none of them actually can travel faster than the speed of light, and it's an observational fact. But we want to do a little better than that. We're theorists, so we want to think like, hey, like really, like what is causing this?
So maybe it might be helpful, Mikey, if you knew like the history of how this had evolved, like starting from like basic Newtonian classical physics to now. Like, why is this such even a question that we're asking?
Yeah, it's a weird question, right? Like, because especially because we're all kind of we grow up learning about what speed is, right? And if you just think about what speed is, it doesn't seem like there should be any limit to it, right? Like I just have to, like, if speed is the amount of distance you travel in a certain amount of time, I just have to travel a larger distance in a shorter amount of time, and then I'll be going faster. So why should this ever become impossible? And I think the best way to think about it, at least it was really helpful for me, is to think about like something that we all take for granted. Like suppose you and I are just standing still next to each other and I throw a baseball. We would both agree that that baseball is going, 40, 50 miles an hour or however fast I can. I don't know, how fast is fast for baseball?
You
Like
can
80, right?
you
Let's
can throw
say like
80,
half
90
that.
miles per hour, I think, if you're good.
I'm being generous with myself. But if I was on a train that was moving 80 miles an hour, and then I threw the baseball, I would see the baseball moving away from me at 40 miles an hour, but you would see it moving away from you at 80, however fast the train is going, plus how fast I threw the ball, because the ball is being released already in motion, right? Does that make sense?
Yeah, that makes sense to me. I mean, I imagine like, yeah, you're moving and the thing that you're throwing is also moving along with it. So both velocities added together.
Yeah, right, exactly.
If I was standing outside.
In this picture, it should be clear that I can go faster than the speed of light, right? All I have to do is be on a train that's going a little slower than the speed of light, and then I have to throw a baseball that's also going a little bit slower than the speed of light. Then you'll see it going, almost twice the speed of light, right? Because the velocities add. But the strange thing is that that's not what happens. what ends up happening in observation is that if you're on a train going really, really fast, if you actually shine a light beam instead of throwing a ball, then you're basically throwing some photons at exactly the speed of light, right? And it turns out that no matter how fast you're going, I cannot view those light beams as moving away from me any faster than the speed of light. So even though you know you're going really, really fast and you're throwing things at exactly the speed of light, if I view that same thing, that same event, I'm also seeing those photons or whatever, going at exactly the same speed of light. So it's not just that it's like this barrier that's hard to get across. It's like we both think that you're throwing the photons or whatever faster than the speed of light, according to me. But when we actually look at the data, we don't see that. So it's like this weird conundrum.
Huh. I guess like then my natural question is what changes if the speed of light is the same no matter how fast, in your example, the train is moving, then something else has to change about the situation. What would that be?
Yeah, exactly. Something else has to give, right? Like there's no way that otherwise there's a paradox. And it turns out that at least in one perspective, the faster you go, the more space shrinks from your perspective. And that's what kind of balances the whole thing out, is that we actually disagree on the amount of space that was traversed in the same amount of time because the actual space is shrinking. So people, you and I, if we're going at very different velocities with respect to each other, we have a very different perspective of the world. If you were traveling close to the speed of light, you would see my world, space stretched almost in the shape of like a pancake. And then it wouldn't be any kind of a question as to why we're having this kind of disagreement.
Yeah, and I guess to add, this is sort of why Einstein was very famous to come up with this idea that, I mean, it's not only Einstein, that basically space and time are relative, and there's also there's these sort of conversion factor between you and I, the amount of space. I mean, ultimately, speed is just the amount of space that you perceive an object travel given an amount of time, right? And then relativity tells you that depending on how you're moving, that conversion factor can change. Space can convert into time, time can convert into space, and in such a strange way that ultimately that light always travels at the speed of light. So that's sort of one of the first, I guess that's one of the first experimental evidence, right, on the strangeness of space-time, and it's evidence that something more odd is going on.
Wait, I want to take a step back there from what you said. What do you mean like space is time and time is space, or what? Maybe I misheard you. Can you repeat that?
Yeah. So basically, we comment that like if you carry a flashlight around, whether you're on a train, on an airplane, or in the next galaxy nearby, shining that light, doesn't matter who's measuring the light that's coming out, and doesn't matter how fast you're moving. Everyone will measure that the light coming from your flashlight moves at the speed of light, right? And it seems like a simple fact, but it's very weird because that intuition doesn't work. For example, if you're moving on a train, you throw a baseball, like Mikey's saying, like the velocity is not always you throw at 95 miles per hour. It's not always that. It depends on how fast you're moving. But for light, it's an experimental fact that it turns out that it's the same. Doesn't matter how fast you're moving, whether it doesn't matter you're moving away, you're moving toward me, you're moving at an angle. It happens to be the same. So that means the basic intuitions of adding velocities and speed, it doesn't work, right? But then that logic is so intuitive to us because it's just like, hey, if you're on top of the train, you move more speed, you move more space in the same amount of time. Like how come that speed doesn't add, right? But then what gives is that the amount of space you move actually changes, and also the amount of time that elapses also changes. and these two can compensate each other, right? Ultimately, the speed is the ratio of these, right? And they can like for example, if you in this moving on flashlight on a train scenario, right? Let's say it's the same amount of time, but then the amount of space that move changes. You say, well, then it's got to be faster, right? Like it's more space, less time, right? So the speed is more. But then, from the perspective of the person on the train, that it turns out that amount of distance actually changes. It's not what you think. So it shrinks. So it shrinks, and also time also changes. It shrinks and expands in such a way that, hey, that ratio remains constant for the speed of light. That makes sense.
Yeah, so just to summarize, basically, if you look at objects like baseballs, right? Everyone disagrees on how fast they're moving, depending on if you're in a train or if you're in a couch or if you're on another planet. Everyone will disagree on how fast a baseball is moving. But everyone in the universe agrees on how fast light is moving. And so that's like totally bizarre, right? Like from a historical perspective, people notice this and it's like, what gives? It's like, is there some like discontinuity? Is there some break here? And it's not. It turns out that as you travel faster and faster and faster, close to the speed of light, space and time literally stretches itself in order to accommodate the fact that the speed of light can be agreed, that the speed that light travels can be agreed upon by everyone in the universe. It's bizarre.
And when you say everyone in the universe, like are there any limitations to that, or just like observers, or what? Just want to call that statement.
So no, this is actually one of the I can say with 100% certainty that everyone in the universe measures the beam of light going at exactly the same speed. It doesn't matter. It's like the one universal key that we could have to communicate with people who are different frames.
I suppose there's one caveat, right? Like it's possible that there's no proof whatsoever, but it's plausible. It's not totally crazy that maybe light doesn't move at that cosmic speed limit. Okay, if that were true, then it's possible that you can catch up to it and see that light slows down, right? But if light indeed travels at the cosmic speed limit, which happens to be like the speed of light so far, right? Because we have never measured a photon slow down, right? But if that were true, then yes, the speed of light is the cosmic limit. Then yeah, the beam of light will always be at the cosmic speed limit, no matter who watches it.
Wow, that's pretty amazing. I do remember us mentioning on a previous episode, few episodes back, about if you had a massless particle that moved at less than the speed of light, it might as well not exist. So, like, it's a coincidence. Is it a coincidence that the photon is massless and it moves at the speed of light, or is that just the feature of nature?
I kind of remember that. If a massless particle,
that's definitely not a coincidence, right? Like, yeah. So there's another leap of logic here. Going from space-time to mass and energy. There's another conceptual leap, right? So I'm not sure we should go into that, should we?
Fair enough. Let's avoid it. Let's avoid it for now. We can
come back to it later. There's a conceptual leap, but we can talk about that.
Yeah, I think my question was centered around, is it only light that has this cosmic speed limit property, or are there other things? Like, is it specifically because of light, or is it more general than just light?
So that actually goes back to what Tim was saying, is that, what we're calling the cosmic speed limit is the speed at which anything that has no mass has to travel. This is why we call it the cosmic speed limit, actually. So people used to call this the speed of light, and this somehow makes it seem like light is special. But it turns out we call it the cosmic speed limit now because it's not just the speed of light. It's the speed at which any particle has to travel if it doesn't have any mass. light is one example of a particle that doesn't have any mass, but there's a lot of others. And any particle that doesn't have mass travels at the speed of light. So yeah, it's kind of dissatisfactory naming convention.
Yeah, maybe we can kind of go a little deeper in that train of thought. So the beauty of Einstein's theory isn't just saying, oh yeah, things are relative, space converts into time. There's actually a very concrete framework to talk about everything relativity related. And Einstein brings to us this language of symmetry. Basically, it tells you that when we say conversion, we really mean a sort of relationship that space and time are related to each other. Just like how, up, down, left, right, front, back can be related to each one another, right? Like imagine my front is pointing toward the screen, and if I just move a little bit, my front will become my right, right? Or if I duck my head down, up will become the front will become my up, right? So Einstein extends this notion to say that, hey, even time and space, depending on how you move, they can be converted into one another. And in this way, the structure of space-time now comes with a symmetry, that the symmetry will mold the structure of space-time. Like if you believe that the axiom of the universe is dictated by this sort of this beauty of this symmetrical relationship, then this idea of the cosmic speed limit actually comes very naturally.
Huh. Um, can you summarize that a little bit more?
Yeah, so it's almost like how'd I put this? It's almost like, what's a good example?
I mean, I think the basic summary is that so when we're talking about how you have this paradox about like relative velocities, and so that something has to give, space and time have to stretch. This is actually exactly analogous to how when you rotate around in the axis of a coordinate system, your definition of x, y, and z can stretch kind of in and out of each other, and they can mix. Yeah, that's the basic point.
Yeah.
So you can transform your space.
Yeah, and it also tells you something about like velocity. Basically, Einstein tells you that velocity is not really a well-defined concept, right? Like it's like, sure, I'm moving at 5 miles per hour relative to you, but hey, look, the Earth is spinning around super fast. If someone's on Mars, they'll see that, hey, Tim is moving like hundreds of miles per hour. Or imagine you're looking at the rotation of the galaxies, like I'm moving at like, I don't know, bazillion, well, maybe not bazillion, but many, many miles per hour very quickly, right? So it tells you that, hey, this notion of how fast you're moving doesn't really make sense to some extent, right? So Einstein, so in terms of this symmetry, it tells you that instead of talking about velocity, Einstein's the symmetry argument allows us to group particles into different categories that are actually concrete, right? So using the symmetry argument, things are actually grouped into 3 categories. So there are things that move slower than this cosmic speed limit, okay? And no matter how you look at it, how fast you move, they will remain moving at the slower than the speed limit. Okay, and there are objects, theoretical objects, if you imagine them, that can move faster than the speed of light, this cosmic speed limit, right? And no matter how you move, how you're on a train on Earth, they will always remain moving at the faster than this cosmic speed limit. And then things that move exactly at this cosmic speed limit, no matter what you do, will always remain exactly at that cosmic speed limit. So Einstein's theory allows us to categorize objects into 3 categories, right? At the speed limit, below, and faster. And the thing is, because of symmetries, these cannot mix into one another. They are distinct categories. Once you're in one category, you're stuck.
Wait, you can't move. So I can't move to a different category if I wanted to.
Yeah, unfortunately, you can. It's like if this symmetry holds, if this symmetry holds, it's almost like imagine. I guess a good example. I guess a good example would be like a sphere, right? Imagine you draw a sphere, and your symmetry. Symmetry is basically it's like what are the types of movements that you're allowed to have. Like imagine you draw a sphere. The sphere has radius 1, right? And imagine I'm on that sphere, and Sahil, let's say you're on a different sphere, radius 2, right? And imagine the only movement I'm allowed to have is to rotate around, right? Or someone is rotating around. Like I'll never reach you, Sahil. I'm on the sphere with radius 1. I can never touch the sphere at radius 2. If you rotate around, Tim will just be rotating around that sphere around and around and around, and you just never be able to touch radius 2, right? And so relativity is somewhat like that. So it's what we call what's the name? Like spheres or like just I guess ordinary geometry? Like the relativity is a little special. It's called like hyperbolic geometry. And these categories are kind of like spheres, except that now instead of talking about radius, we have these like speed limits, right? Like at the speed limit, below speed limit, above speed limits.
I see. And so what you're saying is it divides up to these distinct categories and they cannot mix if the symmetry of this theory is to be obeyed? Is that
Yeah, exactly. Yeah. So I think the symmetry is key, right? Like so if you can't cross it, just like how I can't cross into Sahil's realm of radius 2, if I'm at lowly radius 1, I can't cross, then particles that are slower than the speed of light just kind of is stuck in that realm. Just cannot cross. You can get close, but not quite.
Oh. Oh. I guess then like well I if this is like too far off topic question, let me know. But one question is like, what if crossing was allowed? What could happen? Or like what would that mean? That symmetry was not respected.
I mean, I would say that okay. When I say crossing, I mean like if you just change your perspective, right? Like of course in that spheres example, like if you just rotate your head around, obviously, I if I'm living on like a sphere radius 1 sphere, I can never go to the radius 2 sphere. But of course, you can just say, hey, if I just move around, I just go beyond the movement that you restrict me to. Like Tim can obviously reach Sahil if I just walk, right? So I suppose you could kind of theoretically force that to happen, but then it has to be some kind of really violent interaction, right? It's not. I'm not sure what that would look like. Like I suppose that like a particle could decay into particles of light, then this crossing, I guess, would happen, right? Potentially, and maybe you can kind of imagine a particle decay into particles that move faster than the speed of light, but that's a slightly different story. But that doesn't really work. But it goes, but that's a little beyond just theory of relativity.
So more speculative.
Yeah, that's definitely speculative, and it doesn't work in multiple ways, I think. I don't know. What do you think, Mikey?
I don't know. I'm wondering what is.
Too crazy for your thinking?
Yeah, I was trying to think of how to clarify the definition of what a symmetry is, because we've been talking about it a lot.
Yeah.
But it's not exactly clear what it means, probably to a lot of people. Yeah, that's a toughie.
Well, like, I mean, if I'm looking at the fan above your head, it has like a certain kind of symmetry to it.
Yeah.
Is there any way you can explain it in terms of your fan above you?
Yeah, no, because yeah.
I mean, can we describe it in terms of light cones and stuff. I mean, this is hyperbolic geometry. Like the ordinary geometry, you talk about circles and spheres. These are the symmetrical objects in the ordinary Euclidean geometry, right? But when we talk about hyperbolic geometry, we talk about parabolas, hyperboloids. Those are the objects that we care for, and the cone, if people have studied like high school level physics, the cone is like the conic cone is like a special object, and that's related to how if I look at beam of light and look at how they travel, it traces out kind of the light cone that we refer to. So light cones and paraboloids and hyperboloids, these are the objects of interest in special relativity, and I think you can understand some of the issues from this perspective, but also it's high dimensional, it's 4-dimensional like geometry. It's kind of hard to visualize by itself, so I don't know how to describe it properly, I would say.
That's fair. That's fair. I mean, this is a 4-dimensional space, so difficult to draw. Yeah, I would say so because of the symmetry, we cannot exceed the speed of light, and light can't change its speed. It's just what it is.
Yeah, and I think, to me, I think relativity, like relativity doesn't necessarily forbid something to travel faster than the speed of light, and I think, Mikey, you might disagree. I think relativity just says that there are these three categories of the slow movers, let's say, and the speed limit movers, which is like light, and the faster than light travelers. This is all theoretical, of course, right? There are these three categories, and it's just that they cannot cross into one another. They're just distinct.
But
right?
it's not just theoretical. It's true. I'm trying to think of a way to convince the audience why they should believe what you're saying. They're just like parabolic geometry, blah.
Yeah. Yeah, I know. I spent a lot of time thinking about it, but it has to do with the fact that paraboloids and hyperboloid, they are like in some cases they're like disjoint pieces. Sometimes they wrap around. It requires at least some level of high school, like you remember like quadratic equation. You draw these curves, like like some level of understanding on that, and that's a little technical, I think.
So, Mikey, have you thought of a way to convince the audience?
Yeah, I mean, it's true. Everything as Tim's saying is true. Is that it does? There's these disconnected pieces, but why should that convince your everyday person that you can't go faster than the speed of light? Is having trouble summarizing.
Well, at least it's slightly less leap of a faith to accept that there are these three distinct categories that you cannot cross. I know it sounds arbitrary, right? But it's a slightly weaker statement that the slow movers, the speed limit movers, and the fast movers, you just cannot cross into each other's territory, like easily at least, right?
I guess the main point of this is that it's not like there's like some person, when I try to go faster than the speed of light, there's someone pushing me back. It's actually what we call a geometric obstruction. So if you look at the sphere, there's no obstruction. I can point in any direction I want to from any other direction just by rotating. Right? There's nothing obstructing me from changing my perspective. But these three disconnected components that Tim was referring to come from a kind of geometry that's a little bit different from a sphere that does have these three disconnected components. So it's not like there's some force that's preventing me from going faster than the speed of light. It's literally a much more fundamental restriction than that, like equivalent to a restriction of like being, coming from geometry. Oh, I don't know. That's satisfying.
I mean, like if you try really hard, if you try really hard to accelerate, like you just hit the gas on a spaceship, you're like, man, I'm gonna blast off to the speed of light, right? Like in terms of these geometric objects, you're just riding on the asymptote of a parabola. I don't know if that's the right word. You're just asymptoting, getting closer and closer to the speed of light. And trust me, you're gonna feel that acceleration. You're gonna feel like you're moving really, really, really fast. But yet, the conversion rate, it's just like not in your favor. It's almost like a tax, basically. You're just kind of stuck in this asymptote, just getting closer and closer, but never actually quite get there. But yeah, you're moving fast. You're moving fast. I'll give you that. But it's just you can't cross that horizon actually, and the horizon is actually a good word, because it's almost literally like a horizon, like a cosmic. They call it the Rindler horizon that you cannot cross as you try to accelerate past the speed of light. So.
Wow. Um, huh. So there's this like cosmic horizon that we cannot cross because you have to be moving faster than light to actually cross it.
Yeah, basically. So you can do this theoretical exercise and look at let's say from the perspective of me trying to go fast, trying to beat this limit. Let's say I'm like, screw this, I'm gonna go as fast as I can, try to beat it, and hit the gas and accelerate as much as I can. The maximum amount of acceleration. You can say, well, what's gonna happen to Tim? What you actually undergo is you're gonna see space-time in a very different light, right? Because and as you go faster, things in front of you is gonna blue shift. It's gonna be more and more energetic, and things behind you is kind of fade away. And you also experience this phenomenon called the is it the UNRWA radiation? You actually see particles getting created out of the vacuum. And this is very similar to Hawking radiation. It's very similar to like near the horizon of a black hole. It's almost like you're gonna tunnel, like you can't quite hit it. It's almost like you're in a black hole. You can't quite hit that cosmic speed limit. You can try, and the more you try, you're gonna get smacked by radiation. And ultimately, if you hit the acceleration, if you try to max out the acceleration as much as possible, you're gonna burn to a crisp. So like physically, you will, like, I'm sorry to say that your attempts will be futile. So
Wait, what? Why do particles get created as like you move faster and faster? What is that? Why does that happen?
yeah, it's because from your perspective, space-time becomes curved, and this curvature sort of, oh, it's very technical, right? The vacuum structure changes, and it's literally particles popping out of the vacuum that you're getting hit, and
Oh, so it ain't happening. Is what you're saying?
yeah, like I think it's just that no matter how you slice it, you can try to cheat and say, hey, can I get to that speed limit? Physics has a way of stopping you. Basically, it's like, nope, like not happening. Nope, not happening.
Wow. Is there any way we can speculate about what it would be like to move at the speed of light? I think Tim, we did an episode about that a while back.
I
Yeah, we
think
know exactly. Like basically, so when you're moving at the speed of light, um, I mean, as you approach the speed of light, you think you're getting faster and faster and faster because you think you're traveling a longer distance over a short amount of time. But actually, the space is contracting, so you're actually not traveling that much distance as you thought you were in that amount of time. And if you actually go to the speed of light, that's the point at which space actually contracts down all the way to literally a flat disk. So we can't speculate what it would be like to approach the speed of light and reach it. And basically, it would look like the universe is going from a sphere down to a disk along the direction that you're moving in. And then you're not actually going that fast because you're not going that far.
wait, and I wonder if we really try to force the math to go through. If you go faster, is it going to be analogous to going through a black hole? It's almost like a tunnel, and all of a sudden it flips. I think it is, right? You go to the rim of the horizon, and all of a sudden it's almost like you're at a different universe. But then there's a wacko thing that happens when you are faster than the speed of light. Einstein's theory tells you that causality becomes weird now. Like events that happens, like for example, the fact that my grandma was born before me, like that fact is true no matter who you are, as long as you travel, as long as you move less than the speed of light. That fact does not change. Okay, that's a true fact. But if you are moving faster than the speed of light, actually that fact could change. From your perspective, it could happen that be like, hey, my grandma is born after I was born. So then it becomes wacko. But then this is like the alternate universe. I don't know. This is like a fake news universe. So more reason that like more reasons that this shouldn't happen, basically.
Wait, is there an easy way to understand why the causality doesn't hold if you move faster than light?
Yeah, I think it's almost like, can you visualize this way? I'm not sure if this is right, Mikey. It's basically like the universe shrinks down to a pancake, and then after it goes through because the universe has some depth, but then length contract, it becomes a pancake and becomes really degenerate. And if you really force your way through all the math and all the theoretical nonsense, that you force your way through, I think space just kind of becomes degenerate in some ways. Yeah, I'm not sure how this.
Basically, when space becomes a disk, all these points become the same point. So.
Yeah, at some point, yeah, you cross this degeneracy already when you hit the speed of light, because it becomes a pancake, crush, and then now all the events kind of just scramble up in some weird way. I'm not sure how to describe it, but this doesn't happen anyway. So.
Yeah. Well, I realize we have gone way over time, and so anything you want to end with before we head out?
Geometry, yeah, that's the reason why. We said a bunch of things here that we didn't explain, but yeah, I guess the point is that it's a geometric abstraction, and it's the nature of our universe.
Yeah, yeah. To some extent, I'm not sure how to put it in a more elegant way. Yeah, ultimately, it's down to this fact that space and time are interrelated. One can be converted into one another and vice versa. And this forces a very peculiar structure on our space-time, these distinct patches, and almost give us these bottlenecks and kind of obstructions that, like Mikey said, geometric obstruction that you just cannot cross. And it's actually fantastic that the universe is structured this way. It's actually really interesting such a delicate structure exists. And I think that's somewhat unexpected, right? This is like a extra symmetry that Einstein discovered that we didn't know existed. So and nature is taking full advantage of it. It's fascinating.
All right then. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
All right, see you all next week.
Yeah.
Yep.
Bye.